The ground beneath our feet feels immutable. From our perspective, a mountain range is a permanent fixture of the landscape, frozen in time. But satellite data used to build this map shatters that perception. Tracking the surface with millimeter precision reveals the lithosphere is in constant motion. These velocity arrows plot the progress of massive tectonic plates, drifting in specific, measurable directions. The speed of this movement is nearly imperceptible. Most plates, like those along the mid-Atlantic ridge, crawl at the rate your fingernails grow. Even the fastest, like the Nazca Plate, only match the growth rate of human hair. This creates a fundamental paradox. We live on a fractured shell moving at a microscopic pace, yet this slow-motion crawl generates the planet's most cataclysmic events. We see the reality of that paradox when the crust finally yields. This collapsed highway overpass in California is the immediate result of a plate boundary suddenly overcoming decades of resistance. This destruction is part of a continuous cycle. These streetcar tracks, warped and buckled during the 1906 San Francisco earthquake, show how the rigid crust has been failing under pressure for centuries. These failures occur because tectonic plates have jagged, rocky edges that do not glide smoothly. Instead, they get stuck, causing the plates to lock together while the deep forces behind them continue to push. When the friction finally fails, decades of microscopic creep translate into seconds of extreme seismic shockwaves. The built-up pressure snaps, forcing the ground to displace by meters in an instant. The crust is essentially a loaded spring. It accumulates potential energy over generations until a breaking point triggers a violent kinetic release. To find the source of that energy, we have to look beneath the rigid plates and into the asthenosphere, a layer of the upper mantle where rock is hot and ductile enough to flow. Here, the Earth operates as a massive thermal engine, driven by mantle convection. These laboratory patterns show exactly how these convection cells function. The dark nodes represent cold currents sinking back into the depths, pulling surface material down with them. This is the mechanism of slab pull. As the cold, dense edge of an oceanic plate sinks into the mantle, gravity drags the entire slab downward. That weight provides the primary force that hauls the continents across the globe. The shifting plates on the surface are the visible manifestation of this deep thermal churn, the rigid top layer of a planet-wide convection system. This deep energy manifests at three specific types of boundaries. At convergent boundaries, plates collide head-on, compressing the crust until it has no choice but to buckle upward. The Himalayas are the direct result of this continental thrusting. These jagged peaks represent millions of years of rock forced upward by a relentless collision. Along transform boundaries, plates grind laterally past each other. This linear scar marks where the crust is held in place by friction, waiting to snap. Finally, at divergent boundaries, the mantle's engine pulls plates apart. This creates rift valleys where the crust separates, allowing molten rock to well up. These boundaries are the primary zones of transition, where the relentless mantle forces the rigid surface to bend, break, and bleed magma. While we can witness the destruction of earthquakes on land, the vast majority of divergent tearing occurs invisibly. Most new crust is created in the crushing, dark depths of the ocean floor. In early 2026, scientists deployed the OHA geodams experiment at the southeast Indian Ridge. Their goal was to use hydroacoustic sensors to monitor an active spreading center in real time. By recording these deep-sea displacements, the team hoped to document the transition from slow thermal stretching to the active formation of the ocean floor. Based on existing models, the sensors were expected to record a steady, microscopic expansion of only a few centimeters over the course of decades. Instead, they captured a sudden, violent burst of movement. In a single episode, the seafloor displaced by several meters, unleashing decades of tectonic tension instantly as a jagged fissure tore through the rock. This opening allowed magma from the asthenosphere to flood upward. As the molten rock hit the freezing ocean water, it blackened and hardened, creating a brand new section of planetary crust. These rapid bursts of creation prove that the Earth operates as a massive, self-recycling system, perpetually forging its own skin to accommodate the movement of its living interior.